All right, this lesson's on single slit interference. We've just finished double slit interference, and we've started to look at some interference patterns with how double slit fits inside of a single slit. Now we're going to focus on why is there interference within a single slit. So this goes to topic 9.2, where we're going to understand and explain the diffraction of light incident on a single slit. We're going to describe the effect of slit width on the diffraction pattern. We are going to determine the position of first interference minimum, and we are going to qualitatively describe single slit diffraction patterns produced from white light and from a range of monochromatic light frequencies. So something to be careful of, monochromatic just means a single color or single wavelength, such as like 636 nanometers. This is very similar to the double slit interference lecture and concepts, with just one minor tweak that makes things a little weirder, but still has the same process of determining the interference pattern. So first I'll have a question of what would you expect to see from sound passing through a single slit? So if we had a screen and my question was like, what would be the interference on this screen? What would be the intensity on this screen? If you were to be a little person right here and just like walk down this line, where would you hear the most intensity? Where would you hear the least intensity? And you would imagine as a sound wave that the intensity should decrease as you get further away from this center point, right? From the center point right here, where the max should be right in the middle. And you get that from the idea that the intensity is inversely proportional to the square of the distance. So then, if I were to ask you the same question, but instead of sound, now it's light, what would you expect to see from light? You might say the same thing, where you might say, yeah, well, it's passing through a slit. I'll see a maximum in the middle, and then should decrease because the inverse square. But we have just seen that light does not act as a particle. It doesn't act like sound all the time. There is strange interference that's occurring, and the same type of interference occurs when there's a single slit. And we've already seen this from the previous video when we compared single slit patterns to double slit patterns, except the single slit does have this more intense middle, or it's a larger intensity in the middle, and then it breaks up and has these small destructive interferences, more destructive interference right here. And we saw this as a single slit envelope over a double slit pattern. But now we're just going to focus on the single slit pattern. Why does this single slit pattern occur? Why is there this large central maximum and these very, very dim minimums? And this has to do with what's called Huygens principle. Huygens principle is a construct that has been made that helps us understand why this occurs, but it's a little bit far-fetched to say we are for sure certain that this is exactly what happens, but it is a good construct for us to understand how this interference pattern occurs. So to make sense of this, I'll first give you the definition and then we'll think about it. So all points on a wavefront of light may be regarded as new sources of wavelets that expand in every direction, and the tangent line of all the wavelets produce the new wavefront. Okay, what the heck are wavelets? And what do you mean by this tangent line to the wavelets? So let's first look at this straight wavefront right here. And let's identify the points on this wavefront. So we're going to focus on just this A wavefront, which is like the initial wavefront. And I'm going to identify the points. I've got a red, I've got an orange point, I've got a blue point, I've got a purple point, and where are the wavelets on this? Well, wavelets are just another word for wavelet is like a wavecito, right? A small wave. And that wave is expanding outward on each point. Now, when we say each point, technically we do mean like if there's an infinite amount of points on this wavefront, but obviously we can't draw an infinite amount of points, so we just draw them evenly incremented for us to make some sense of this. So if I were to look at the wavelet that's expanding from this red point, I would look at this wavelet right here. If I were to look at a wavelet that's expanding from this orange point, I would look at the wavelet that's right there. And if I were to look at the wavelet from the blue, I would look at this one, and so forth. Keep on going down. Ooh, purple will be that one. And you can see that if I were to look at all of these wavelets as they're expanding outward, the tangent line across all of these wavelets create what's called a new wavefront. And this is happening over and over and over and over, which is kind of weird. That's why it's not exactly, we don't know if it's exactly happening. But a wavefront is being created, and then at each point on the wavefront, wavelets are expanding outward, and the wavefront is moving forward. One thing that's important is the wavelet can't move faster than the wave because it is a part of the wave. So these wavelets are moving at the same speed of the wavefront, and you imagine that it's just radiating outward and the wavefront's moving forward. It happens both with straight wavefronts or with circular wavefronts. Or if I say, here's my point on my circular wavefront, I can draw my wavelet coming out from there, and as I move around the circular wavefront, I draw these other wavelets that are expanding outward, and they would be expanding with this circular new wavefront. So to use this in other forms, such as refraction or other light behaviors, might help us understand what's occurring, and I think it's best to be seen in an animation. So I first have this animation, and I'm not sure if you're going to be able to make sense of this just by looking at it once. So we're going to watch this, but then I'm going to take you through what's actually occurring. So in this animation, there are wavelets that are expanding outward from the medium. So we're only looking at the wavelets that are expanding out from the medium. We have wavefronts coming into this water, and then they are refracting and reflecting, and the wavelets are only traveling as fast as the medium allows the wave to travel. So the light wave travels slower in water. And so you can see how the wavelets are traveling slower in water but faster outside. And that's why you can see a wavefront that is being bent as it travels into the water. Now let's go to this animation and make some more sense of it. All right, here we are. I'm going to go to the next step, and you can see each of those points on the medium right here are going to act as the source of a new wavelet. You have a wavefront that's coming into the medium barrier, and it's going to be reflecting and refracting. And as it interacts and reflects and or refracts, that's when we are looking at the wavelets, the source of the wavelets. So we're going to even go a little further. There's a lot of steps to this, trying to make sense of this. So we have this wavefront, and remember, a ray is perpendicular to the wavefront. So the ray is actually coming in this direction, and it's going to be reflecting out in that direction. And then that's where you see this reflected wavefront. This blue line is the reflected wavefront, showing that the ray is being pushed outward at an angle of 45 degrees. And then you can see the refracted ray is being bent inward. And then this is shown with this picture where we have a incident light hitting a barrier, and then a reflected light bouncing off at the same angle, and a refracted light that's transmitting through at a smaller angle. So I'm going to pause it at some point in time right about here. And so you can see that this wavefront was coming in, hitting this point, and actually hitting all of these points. And then you can see the reflected wavefront and the refracted wavefront as shown by Huygens' principle from each of the wavelets traveling at the same speed that the light would travel in each medium, and thus creating these new wavefronts that are passing forward. Now I did say now technically it would be like happening over and over and over again. So this is a simplified version where we're only looking at the sources of the wavelets on the medium, the boundary. And then it goes even further if we want to watch this. It shows multiple wavefronts coming in. So these are all coming in, and they will all be reflected and refracted. Now, technically, this is what is really happening. If we were to see like the sunlight beam onto water, there would be technically an infinite amount of wavefronts coming in because the sun is shining on it. And then you would see the reflected light and the refracted light. And by looking at that, reflected light, you can see the reflection, and so that's where what we would be seeing. Now it gets overcomplicated, so let's go back. So how does this help us understand how single slit interference occurs? Well, let's first focus in on the slit itself and saying when we zoom in on the slit, because these slits are really, 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 really small, each point on the slit would act as its own source of a wavelet, and that wavelet would actually interfere with each other. Now, when we're just, if the slit's wide enough, then it just turns into a new wavefront. But when the slit gets small, we understand that diffraction occurs around the sides and it expands outward and there are points of interference at each point along this slit. And the interference pattern we would see would be something like this, where the central max would be the largest. And in fact, it is about 20 times larger than the first maximum. So this orange point is like its first maximum, and that would be about 5% of this original central max. So this is your central max, and this is your first maximum. And then it decreases even more. It's like 2.4% and 1.2% or something. But all you really need to know is that first max after, which is 5% of the original intensity.
All right, there's a few more things you'll need to know regarding the intensity. And that is that this max intensity I naught is proportional to the square of the slit width. So B is the slit width. Conceptually, this makes sense because if we were to enlarge the slit width, more light would be able to pass through, and you would also see less diffraction occurring. So there'd be more intensity in the central max.
All right, now I'm going to zoom out because this requires us to look at a big scale. Now, technically, this screen, which we see on the right, should be very, 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 very far away from our slit in order for us to get small angles that this interference pattern could be observed. But in this case, I have to kind of put it closer just to make the math easier to make sense of. So of course, there's a first thing we need to know, and this should look exactly like the double slit, except we are in the single slit world. And so this distance is capital D, and then we need to identify which point we're looking at on the screen in which it causes interference. And I'm going to look at the point that causes the first minimum, and that's where I told you would be the difference between single slit and double slit is in single slit we look at the first minimum, whereas in double slit we look at the first maximum. There's a reason for that, and we'll be able to show you that. So that means that half of the central maximum has some distance s. We're still using s, and that's where the confusion could be in. Something to note right there is that means that the distance on the opposite side of the maximum is also s. So the distance between the central maximum, or a distance of the central maximum, is 2s.
I'm also cutting in right here to say that the distance between the central max and the first minimum is s. That also it's also true that the distance between each following minimum is the same distance, s. So we would see these distances continue as the same distance as the central max to the first minimum, as shown by this diagram.
All right, but we need to make sense of where we can solve for this s. And that happens right at the slit. So we have this light. It's coming in. If we assume that the slit's small enough, then these waves should be pretty flat when it comes into this slit. I've made it bigger, obviously, because that's how we're going to be able to make sense of this. And I want to look at these points on the slit as the sources of the new wavelet. So I might have made a mistake. I'm missing an orange. That's why what's happening. There's an orange point right here. And so I've identified the points on the slit in which the wave front passes through the slit, and there become new sources of wavelets. And as new sources of wavelets I want to look at the interference between these wavelets. And I'm going to look at the interference between the top one and the middle one. This is maybe a little weird, but trust me, there's going to be a reason for this. So let's look at where it would hit. Well, I need to go to this point where it's go up here to where it's the first minimum, and it's going to come here. It's also going to go to the first minimum. And then, similar to the double slit, I'm going to draw a line right here that is pretty perpendicular. There's some weirdness here, because is it really perpendicular? Can it be perpendicular? We got some problems. But when we're dealing with such small angles and small angle approximation, these approximations actually work when we're only looking at very, very, very small angles. And so we're fine. Now at this point here, we've identified this is, let's make it better, this is our first minimum. And if this is our first minimum, or the fact that it is just a minimum, we know that our path difference should be equal to lambda over 2, or some multiple of lambda over 2. But since it's our first minimum, it's just 1 lambda over 2. So that path difference of lambda over 2 is noted in this triangle similar to our double slit equation, where we have a path difference of lambda over 2. That being said, in order for there to be a path difference of lambda over 2, that means that this line right here on the top is equal to this line. And I wanted to just let you know that there is some mathematically incorrect issue going on here, but due to the small differences in this length, the approximation that we made in double slit about a small angle approximation will work again in this another version of an approximation. And as long as the distance between the slit and the screen is very, very large, as well as the wavelength is really small, then this actually isn't going to cause us too much mathematical problems. It just approximates to about equal. It becomes an issue when we start going to much further, like second, third, fourth minimum, but actually first and second minimum tend to be okay. So if this has a path difference of lambda over 2, and we know that the whole slit, we call it, has a slit width of b, then that also means that this is a slit, like half of the slit width, which is b over 2. And we're going to focus on this triangle right here, similar to what we did in double slit, as well as the big triangle right here, all the way across. And those triangles will be seen below. But really quick, I want to identify, say, why are we only focusing on these 2 points that we drew? These 2 red points. Like, what about the orange points? What about the blue points? What about the purple points? Well, if we know that the distance between the 2 red points are b over 2, and we were to move down and say, what about this distance? Well, that should also be b over 2. I'll get rid of that. And what about the blue to the blue point? That's also b over 2. And the purple to the purple point, that's also b over 2. So this occurrence where there are 2 wavelets that are interfering some distance away on a screen and their path difference is lambda over 2, so they're creating destructive interference, that's occurring for every consecutive pair of points down this slit. So where the orange and the orange are also destructively interfering at the end, the blue and the blue are also destructively interfering, the purple and the purple are all destructively interfering, and every pair of points on this slit is also destructively interfering. Of course, there's issues with approximations going on, but just recognize again that we're dealing with such slight differences because we're looking at wavelengths of hundreds of nanometers, and we're looking at slit widths of in like millimeters or smaller. So we have to kind of accept that this approximation is okay. So as we look at this red triangle and this wiggly blue triangle that I drew, we're going to look at the one that Miss Miller had made prior. But instead of lambda and d, we're looking at b over 2, which is half the slit width, and lambda over 2, which is half of the wavelength. And we have also a similar sine and tangent. So if we're to identify that, hey, tangent of theta is equal to s over d, sine of theta is equal to lambda over 2 over b over 2, which is just lambda over b. And then due to the small angle approximation, we said theta is about the same as sine theta, which is about the same as tangent theta. And I strongly suggest for you to test this out, but it only works with the radians. So if you take your calculator and only use angles less than 10 degrees, so say like use 5 degrees, convert that to radians, and then do sine of 5 degrees and then tangent of 5 degrees. And what you'll find is that those three values approximate to pretty much the same value. All right, so that means that what we have, tangent theta, this is pretty much equal to theta. This is also pretty much equal to theta. And so we end up with the equation that's in your data booklet, which is theta is equal to lambda over b. And this is theta is the angle between central max and first minimum. And that's super important, especially first minimum. That's what that says. And B is the slit width. So this equation right here, that is in your data booklet. But you might also recognize that this is not the only part of the equation here that we know, because we know lambda over b is equal to theta, or is about equal to theta, and that should be about equal to s over d as well. But that's not in your data booklet, so you'll just have to kind of remember that using double slit interference as your guide as well. So far we have looked at how single slit interference occurs. We've used Huygens principle to try to understand how there is interference between wavelets that occur at all points on a wavefront. And when we look at a slit, we can identify the different points that wavelets diffract through the slit, and how 2 points on the slit can create 2 different wavelets that interfere on the pattern, on the interference pattern on the screen. And if we look at the path difference of lambda over 2, we would see destructive interference, and that would create us these similar triangles that we can use to find relationships between the distance to the screen, the distance to the first minimum, and the wavelength as well as the slit width. That's what we've just come up with. But we've only looked at monochromatic light, and we've looked at monochromatic light given some wavelength lambda. But as you increase your wavelength, you're going to get an increased theta that hits a first minimum. So they're going to be more spread out the larger the wavelength. So let's look at, if we just looked at white light, and let's just imagine a slit was below this, creating this interference pattern. We definitely would normally see this more spread out, but this is trying to help us understand how this white light would create this interference pattern. So definitely in the center, all of the light would pass right through and converge and constructively interfere in the middle. But you'll notice that very close to the central max, you'll see a blue light, and that's because blue light has a smaller wavelength, a higher frequency. So as a smaller wavelength occurs, it will have a smaller theta. And then as you go down, the color spectrum, so orange, yellow, green, blue, orange, yellow, green, red, you'd end up with red near the end, and that would have a larger angle than the blue. And then you'd have another maximum, and then another minimum, and then another maximum, another minimum, and so forth. So we'll make more sense of this when we see diffraction grading, which allows us to resolve these images better. But just know that depending on the wavelength, you're going to get a different interference pattern, and it's going to be either more spread out or closer together. All right, let's do the sample problem. We have a screen that's located 5.25 meters from a single slit. The distance on the screen from the center maximum to the first minimum is 1.75 centimeters, and the frequency of the monochromatic light passing through the slit is 5.66 times 10 to the 14th hertz. So I know that the screen is located 5.25 meters from a single slit, so my capital D is 5.25 meters. The distance from the center max to the first minimum is 1.75 centimeters. So I have my values. And then I have a frequency of 5.66 times 10 to the 14th hertz, which is not a wavelength. So go ahead. We need to get to theta is equal to lambda over b, which is equal to s over d, and using these given values. Go ahead and work through this. I'm going to pause it, work on it, and show you. So I've used the equation for the speed of light divided by the frequency will give me the wavelength of that light. I ended up with a wavelength of 5.30 times 10 to the negative 7th. And then I would use this equation with the given values to get to my slit width, where my slit width would be equal to d lambda over s. And that gives me 5.25 divided times 5.3 times 10 to the negative 7th divided by 0.0175. And that's 1.59 times 10 to the negative 4th meters. So it's at 15 millimeters. So very, very small. Now I have two more questions that will deal with proportionality. So what would happen to the distance from central maximum to first minimum? So that's theta or s, if the frequency of the light decreased. Well, if the frequency decreases, we know that that means that our wavelength is going to increase. And then due to the equation that we just solved for, if that increases, then we know that theta increases or s increases. So s is going to increase. And so we know the distance from the central max of the first minimum is going to increase. So that's our answer there. If our slit width increased, well, I see that my s is inversely proportional to my slit width. So if my slit width increased, then that means that my distance between my minimum is going to decrease. And that's it with this concept and problem. See you in class.